idea here, okay, so the idea here is that there's a pretty large overlap between the user base of these three networks. So one can imagine that if you combine information from all three of these networks, you can get some additional information that allows you to improve community recovery algorithms. Now, the key challenge here is how exactly do we combine the information across these networks? And this is actually a pretty non-trivial task. So one thing you can think about is that user level information might not be the same across these various networks. For instance, if the same individual is a member of all these networks, they might have different usernames across the networks, which can make it hard to aggregate their information. And more generally, we expect that information about users across these networks are similar, but not identical. And this is because different networks capture different aspects of social behavior, with Facebook and Twitter capturing more personal interactions and personal information, whereas LinkedIn captures professional information. So more generally, addressing this key challenge of properly combining these data sources is going to be a fundamental step in how we can leverage multiple networks to improve community recovery. All right, so to talk about this more mathematically, let's think about a model of correlated networks, specifically correlated stochastic block models. So the way this model works of generating correlated networks, we start with a given stochastic block model. You can think of this as a base graph. And then we're going to construct two graphs, G1 and G2 prime, by sampling edges from G independently with probability S. Some edges are sampled by both graphs, and some end up in one graph but not the other. And there are also some edges that don't end up in either G1 or G2 prime. Right, so this subsampling procedure captures the fact that the two networks G1 and G2 prime have many similarities in their structure, but they also have several differences as well. And that sort of captures the ideas I was talking about on the previous slide. All right, so next, the final step in the construction is we construct a new graph G2 from G2 prime by choosing a random permutation pi star and permuting the labels of G2 prime according to that permutation. So the updated graph here is shown in purple. And the idea behind the permutation is that node level information is not always identifiable. And this goes back to the username example. So the reason for applying the random permutation is to really emphasize that the labels of the nodes shouldn't be helping us when we're trying to use multiple graphs to find communities. All right, so hopefully the model is clear. One interesting consequence of the model is that marginally, G1 and G2 are both stochastic block models with parameters n, ps, and qs, where this additional factor of s is due to the subsampling. And based on this marginal distribution, we can apply the previously known results to show that exact community recovery is impossible from either one of these graphs alone if this condition here is satisfied. Right, so this is useful observation out of all this. Now, the key contribution of our work is to study how we can use multiple correlated networks in order to improve community recovery algorithms. So let's talk a little bit more about the details there. So as an example, here are two correlated stochastic block models. The networks that we're given have no labels, and we have no community information a priori about them. And the first step we're going to do is a graph matching step, or vertex alignment. And the idea here is to find a labeling of these two graphs which maximize some sort of similarity score. And we call this labeling an alignment pi hat. This step is commonly known in the literature as graph matching, and it's been widely explored over the past few decades. It's a pretty interesting problem in its own right. There's plenty of applications and various practical works about it, and there's been a lot of interest in it from the probability, statistics, information-theoretic, and computer science communities, deriving fundamental limits as well as efficient algorithms to do this task. All right, so that's sort of the first step of our procedure, this graph matching step. And once we've aligned these networks according to the alignment pi hat, what we're going to do is we're going to simply overlay the networks according to this alignment. And the result looks something like this, where we have a denser network formed from edges that are both shared and not shared across the two networks. And finally, now that we have a richer network to work with, we can run a community recovery algorithm on the synthesized network. And that'll allow us to identify the communities in the network. So let's try and understand when this procedure will actually give us the correct communities. What sort of parameter regimes will allow us to succeed here? And to this end, a useful observation is that if pi hat is equal to pi star, so that is our estimated alignment is actually equal to the true alignment pi star, the synthesized network can be shown to be an SBM with parameters given by n, the number of nodes, as well as p and q given over here. In essence, what's going on here is that this synthesized network is exactly the one formed by edges that were not lost in the subsampling process. All right, so given this representation here, we can make the following really interesting observation, that exact recovery is possible jointly from two correlated networks in regimes where it's impossible from G1 or G2 alone. And to see this, remember that in this regime here, recovery is impossible from just a single network, but because of the stochastic block model representation here, it is possible as long as this condition is satisfied. So using multiple correlated networks does help you out here. Now, to sort of complete the picture here, we need to understand when this is actually possible, when we can recover the true alignment. And this brings us to the main technical contribution of our work, which is the question of exact graph matching. And we show that there's a really interesting phase transition where exact graph matching is possible if this condition is satisfied, and that it's information theoretically impossible if the converse holds. And I'll just give you a very brief picture of the ideas here. The information theoretic threshold here corresponds to the connectivity threshold of the intersection graph between G1 and G2. And the reason for the impossibility result is that in this regime, you're going to have a lot of singletons in the intersection graph. And these correspond to vertices that have no overlapping information across G1 and G2. And it's because there's this lack of overlapping information, it's hard to match such vertices. And so you won't be able to exactly recover the true alignment. And this sort of generalizes, prior work on the Erdős-Renyi case. But the Erdős-Renyi case is actually much simpler than our work because we can explicitly compute some key generating functions that are necessary for the analysis, but you can't explicitly compute these for the stochastic block model. So we had to develop some recursive bounds to deal with that. And I won't go into them here, but I'm happy to talk about it a bit more if there's questions. And all right, just to put everything together, this is sort of the main result here. We can recover communities jointly from G1 and G2 if these conditions here are satisfied. This is the graph matching condition, and this is the condition for recovery from the SBM. And we also prove an impossibility result that if this condition is satisfied, you cannot recover jointly from G1 and G2. Right. I think just in the interest of time, I'll skip over this slide and I'll conclude over here. Happy to take any questions.